Now we will look at two examples of your clock radio awakens you with a steady and irritating sound of frequency 600 Hz. One morning it malfunctions and cannot be turned off. In frustration, you drop the clock radio from out of your fourth-story dorm window. So this clock radio is dropped. It's going to hit the floor. 15 meters from the ground. So H is 15 meters. Assume the speed of sound is 343 meters per second. As you listen to the following clock radio, what frequency do you hear just before you hear it striking the ground? You are the observer, and the observer is stationary. Clock radio is the source of waves, and it is moving away from the observer. So this scenario, the detected frequency will be less than the original frequency of the sound waves, and so will be V divided by V plus V source. Because the source is moving away, the detected frequency should decrease. But what is the speed of the source as it hits the ground? Well, we have the potential energy turning into kinetic energy. mgh is equal to 1 over 2 mv source squared. So these masses cancel. The clock hits the floor with a speed square root 2gh. So I find that the detected frequency should be speed of sound divided by speed of sound plus square root 2gh. So if I plug in the numbers, this will be 600 divided by 343 meters per second, 343 plus square root 2, 9.8 meters per second square, 15 meters, and the answer is going to be 571 Hertz. So this will be the frequency detected by the observer, which is less than the frequency of the clock radio, that is 600 Hertz. Let's look at another example. A submarine, sub A, travels through water at a speed of 8 meters per second. We have a submarine A that travels through water at a speed 8 meters per second, emitting a sonar wave at a frequency of 1400 Hertz. So A is a source of waves. The speed of sound in the water is 1533 meters per second, greater than the speed of sound in air. Remember, because the average separation between molecules is less. A second submarine, sub B, is located such that both submarines are traveling directly towards each other. So B is traveling towards A at a speed 9 meters per second. So in part A, what frequency is detected by an observer riding on submarine B as the subs approach each other? So B is observer. The detected frequency when the source is moving towards the observer and the observer is moving towards the source will be larger than the actual frequency. F prime is equal to F times V plus V observer divided by V minus V source. So in this case, I have to identify who is the observer. It is the speed of sound in water plus the observer is B, the source is A. So I will find that the detected frequency is 1400 multiplied by 1533 plus 9 divided by 1533 minus 8. So if I calculate this number, I will get 1416 Hertz for part A. For part B, the submarines barely miss each other and pass. What frequency is detected by an observer riding on sub B as the subs recede from each other? Now the observer is moving away, the source is moving away, so I have to change the signs in the detected frequency. The detected frequency will be less. F prime will be F times V minus V observer divided by V plus V source. Again, the role of the observer is that of B. The source is A. So I will find that this is 1400 multiplied with 1533 minus 9, 1533 plus 8, and the answer will be 1385 Hertz. Indeed, less than the frequency of the source. Now in part C, while the subs are approaching each other, some of the sound from sub A reflects from sub B and returns to sub A. If this sound were to be detected by an observer on sub A, what is its frequency? So if the sub A is approaching sub B and the sound waves are coming from sub B, so now B is the source and A is the observer. So my scenario has not changed. Observer and the source are moving towards each other. Therefore, the detected frequency will be the frequency of the source B multiplied with V plus V observer divided by V minus V source. So frequency of the source B, it's going to be V plus VA divided by V minus VB. But what is the frequency of the source B? These are reflected sound waves from B. So if I look at in part A, I found that for the sound waves coming from sub A, I have a frequency 1416 Hertz. So the frequency of the source B is 1416 Hertz. So if I look at the frequency detected by A, there will be a second Doppler shift. So this will be 1416 times 1533 plus 8 divided by 1533 minus 9, and you will see that this is 1432 Hertz. It's due to the second Doppler shift. The frequency appears for an observer on sub A to be even larger. So originally it was 1400. When it reached sub B, it was detected as 1416. Now when it is reflected second time Doppler shift, I have 1432